Hello everybody, greetings one and all. This is the final session on our topic of integration for year 12. So I've called it Pure Chapter 13.7. Here we're going to be looking at how we can integrate, not just to find the area between a curve, but also the area in between a straight line and a curve. So things are going to get pretty exciting. But of course, before we do anything at all, we need to start off with doing a quick warm-up of 4 questions, which are here. So here are warm-up questions, as ever, 4 to have a go at. Pause the video now would be my suggestion, and when you're ready, please start the video again so you can see the solutions and check that you're on the right lines and are understanding things. So okay, without further ado, here we go. So, question 1, we've got this graph of y equals x cubed plus 6x squared plus 5x. So by factorising the function, we need to find the x-intercepts a and b. So what we need to do here is to just factorise this as we've been asked, which is fairly straightforward, I'm hoping you'll see. So we've got y equals x cubed plus 6x squared plus 5x. Each of these terms has an x inside, so we can factorise out the x straight away. So we get x brackets x squared plus 6x plus 5, and that will in itself factorise. 2 numbers that add to 6, multiply to 5, that's going to be 5 and 1. So we have x brackets x plus 5 brackets x plus 1. So therefore, the intercepts are given when each bracket is equal to 0. So the intercepts are therefore minus 5 and minus 1. So minus 5 is the leftmost one, so a must be minus 5, and b must be minus 1. So we worked out the intercepts fairly quickly. That's going to help us for warm-up example 2. So using the answer to question 1, so let's just remind ourselves what we got from question 1 first of all. So from question 1 we got that a was minus 5 and that b was minus 1. So let's just fill these in. That's minus 5 and that's minus 1. So we need to find the total area bounded by the function y equals x cubed plus 6x squared plus 5x, this curve here, and the x-axis. So we can call this area A, I can call this area B. So we need to consider it as 2 separate regions, like we talked about last lesson. So let's just think about region A first of all. So for region A, this area is going to be given by integrating the curve between the limits of minus 1 and minus 5. And the function is obviously x cubed plus 6x squared plus 5x integrated with respect to x. So if we integrate this here, again, as ever, when we integrate, we take the variable, increase the power of a variable by 1, divide through by the new power. So x cubed becomes x4 divided by 4. In other words, a quarter x to the power 4. 6x squared is going to become 2x cubed, so we have plus 2x cubed. And 5x becomes 5x squared over 2, or 5 over 2x squared. And again, we're going to do this between the limits of minus 1 and minus 5. So first of all, if we input minus 1 into this expression here, minus 1 to the power 4 is just going to be 1, so that'll give us a quarter. Minus 1 cubed is minus 1, so 2 lots of minus 1 is minus 2. And again, you can use a calculator if you'd prefer here, that's absolutely fine. In fact, actually what I'd recommend. X squared, when x is minus 1, will be 1, so 5 over 2 times 1 just gives us 5 over 2. I'll show you the class whiz way in a moment as well. And then the lower limit, minus 5, is what we subtract away. So this is the input for minus 1. Now we subtract away from this the input when x is minus 5. So a quarter x to the power 4, just practice your quartic numbers. Minus 5 to the power 4, that's going to give you 625. So that becomes 625 over 4. Minus 5 to the power 3 is minus 125. So times that by 2, that gives you minus 250. And finally, minus 5 squared is 25. 25 times 5 gives you 125. and that is still, of course, over 2. And so if we input this into our calculator and see what drops out, we should find the area for region A at least. So we've got 1/4 minus 2 plus 5/2. And from that we're going to minus off 625/4, all in brackets of course, minus 250 plus 125/2. And we should find that we get exactly 32. So this area here is 32. Now I did promise you, I'll show you how to do a legal cheat by using the class whiz. We could have input this straight away. So if we did that straight away, we just use this integral button here. We type in the limits, -5 below, and the top limit is -1. And then we just type in the function exactly as it appears. So x cubed, alpha x, then cubed, then plus 6 alpha x squared, and plus 5 alpha x. And what do you know? If you press equals, you get 32. How easy is that? So you might be thinking, well, why is he bothering to show us this long, awkward way? One main word, understanding. Understand what's going on. That is priceless. Bashing numbers in on a calculator is the easy part. Understanding what's going on behind the scenes is much more valuable. But obviously do bear in mind, this calculator, when push comes to shove, is what you should be using in the exam. But don't tell anyone I told you that. Okay, so that's region A. We next need to think about region B. So region B, look, it's a negative area, and that's going to be between -1 and 0. So it's going to be an area underneath the x-axis. So bear in mind, like we mentioned last lesson, this area is going to come out as being negative. So we need to evaluate this answer as being an area. So I'll talk you through this now. For region B, it's going to be the same integral, only from 0 to 1, of this function here. Because the curve is still the same, so we're still integrating the same function. Now we've already got this expression here, so rather than working it out freshly, we can just use this from before. So we had 1/4 x to the power 4 plus 2x cubed plus 5/2 x squared between 0 and 1. Now, of course, when we input 0 into this, it's all going to be 0. So it's going to be 0 minus, whoops, I meant -1 there, apologies, I do that all too often. So minus the input when x is -1. So when we do -1 to the power 4, that's going to give us 1/4. And of course you might be thinking, well, I've already done the input of -1 here. So if you want to be cheeky and just be quicker, you can use this bracket here and just copy it out again. It's exactly the same as what we input before. So inside this bracket is actually going to be positive 3/4. So what's going to happen when you minus -3/4? That's going to give you, whoops, I might get myself confused. I'll just do it on a calculator rather than just working my pea-sized brain too hard. So minus 1/4 minus 2 plus 5/2, close brackets. We get -3/4. So it gives us a negative area, but of course you can't have a negative area, so we interpret this as being an area of positive 3/4. So therefore the area for region B is going to be 3/4. So we worked out two separate areas here. We've got the area for A, all of this here, And we worked that out from before was exactly 32. So region A is 32, whereas region B, what we just worked out here, was this tiny bit, which is 3/4. So now we can work out the total area of the bounded region, A plus B. So therefore, the total area, total bounded area, is going to be region A plus region B, which is going to be 32 plus 3/4, 32 from region A, and 3/4, which is region B. So the total area is going to be 32 and 3/4. And that's our final answer. 32 and 3/4 is the total bounded area. Question 3. We've got two simultaneous equations, well, one pair of simultaneous equations rather, which we need to solve. So what we need to do here is to input y into the top equation. So we know that y is x plus 2, so we can substitute this for y into the top equation. So what we get there is x squared minus 7x plus y, which is x plus 2, plus 6 equals 0. So let's neaten this up. So you have x squared minus 7x plus 1x gives us just minus 6x. Plus 2 plus 6 gives us plus 8. Equals 0. So now we need two numbers that multiply to give us 8, but when we add them together give us minus 6. These two numbers are minus 2 and minus 4. So therefore, these pair of simultaneous equations have a solution when x is 2 or when x equals 4. Now, of course, the first solution, when x is 2, means that y is going to be 2 plus 2, which is 4. So one set of solutions is x is 2 and y is 4. Or, of course, if x was 4, y would be 4 plus 2, which is 6. And so either we've got x equals 2 and y is 4, or x equals 4 and y equals 6. So that's the two pairs of solutions. Lastly, question 4. Evaluate from 4 to 2 the integral of minus x squared plus 7x minus 6 with respect to x. So what we need to do here, as we do before, is we just take each power of x, increase its power by 1, and divide through by the new power. So minus x squared becomes minus 1/3 x cubed. 7x becomes 7x squared over 2, or 7/2x squared. Minus 6, any constant, we just tag an x on the end. So minus 6 becomes minus 6x. And we integrate this from 4 to 2. And so what we're going to have here is if we input 4 into this, so minus 1/3 times 4 cubed, that's minus 1/3 times 64. Then plus 7 over 2 times x squared. Well, if x is 4, 4 squared is 16. Then minus 6x is minus 6 times 4, which is minus 24. Then we're going to minus off that the lower limit bound when x is 2. So when x is 2, minus 1/3 x cubed is minus 1/3 times 8, because 2 cubed is 8. Then plus 7 over 2 times x squared. 7 over 2 times 2 squared. 7 over 2 times 4. Then minus 6 times x, minus 6 times 2 is 12. So bash that into our calculator, see what drops out, and that'll be our solution. So here, we're going to have, put the brackets in. So minus 1/3 times 64 plus 7 over 2 times 16, then minus 24. And from that, we're going to minus off, again, all in brackets, minus 1/3 times 8. Plus 7/2 times 4. And then minus off 12. And we get 34/3. And again, I hear you cry, what's the class whiz way? Well, maybe you've not said that, but if you're thinking that, I'll show you now just quickly. It's so easy for class whiz. I think too easy personally. I'm just an old Scrooge which thinks you should be tortured during an exam rather than have anything easy. I'm cruel. Anyway, so you press the integral button. Luckily for you, I'm not in charge. 2, 4 of the limits, and we're going to integrate between minus alpha x squared plus 7 alpha x minus 6. And what do you know? Drops out nicely as 34/3. Couldn't be easier. Well, it could. I suppose it could be 1 plus 1, but you're not going to have 1 plus 1 in an A-level exam. So there are warm-up questions completed. Now let's move on to the main course. The main course today, we're going to be looking at calculating the area in between a line and a curve. So, like I'm saying here, sometimes you may be asked to calculate the area between a straight line and a curve. So let's imagine we want to calculate this bounded area here, this region A, in between the limits of A and B. So how would we do that? Just thinking about it in simple geometric terms. So this region A here, area A, if you imagine the whole bit of this graph here, from this straight line, the curved bit and that line, this whole bit below y1 from A to B, and if you subtract this bit of coloured in green, which is just underneath y2, this yellow bit, subtract the green bit, will just leave you with area A, wouldn't it? So that's how we could do it. So all of this underneath y1 minus everything under y2. So area A is just the yellow region, which is the integral of y1. It's the area underneath the graph of y1 in between A and B. Then minus off the green region, but the green region is everything underneath the line y2 from A to B. So the green region could be calculated by working out the integral of the line y2 from in between B and A. So we can take these integrals separately, just integrate y1 between B and A separately, then subtract this integral separately. But because the limits are exactly the same, what we can do here is we can merge this into one integral. So that'd be the same as saying it's the integral from B through to A of y1 minus y2 with respect to x. So in summary, we can find the area of the shaded region by calculating from B to A the integral of y1 minus y2. So like I've tried to illustrate there with the colours, that's because the integral from B to A of y1 gives a total area, this yellow bit, underneath the curve with equation y1, and the integral of y2 between B and A gives you the area below y2 only. So the shaded region is one to take away the other, which gives us the integral of B to A of y1 minus y2 with respect to x. In a different way, you might have been thinking, well, is there a simpler way of doing this? In some ways, yes, there is, occasionally. So if I look at this shape here, this green region, it's actually just a trapezium. So sometimes what we can do is just actually use simpler combinations of areas, not just only using integration, but we can use the areas of simple shapes to help us as well. For example, rectangles, triangles, and trapezia. So in this diagram above, for example, like I've just said, it could have been possible, depending on what the question tells you as it's set out, it could have been possible perhaps to calculate A by evaluating the area under the curve of y1 using calculus minus the area of the trapezium. So you could have just done half this length plus that length multiplied by the width, if you knew that, of course. So it's good to know both ways. So without further ado, let's have a look at a worked example together and put this into practice. The area between lines and curves. So here we've got to work out the area bounded between the straight line y equals x plus 2 and the curve x squared minus 7x plus y plus 6 equals 0. So the area bounded, I'm just going to colour this in for you. We want to find this bit here. Okay, so how are we going to do this? Well, before I carry on, I want to draw your attention back to the warm-up question 3. Have a look at these equations here, okay, and warm-up question 3. What we need to do before we can proceed is to work out between the limits we're integrating between. So we want to work out where these bits intersect. So we need to solve these equations simultaneously, but what did we just do in warm-up question 3? Well, we did just that, didn't we? So rather than do the same thing again, just to speed it through slightly, I've put here what we had from warm-up question 3. The straight line and the curve intersect when x plus 2 equals minus x squared plus 7x minus 6. Rearrange that and solve it, like we did for warm-up question 3. We can now work out that the limits of integration are between x equals 2, where they intersect first of all, and where they intersect again at x equals 4. So what we need to do here is to integrate between x equals 2 and x equals 4. But just go back a moment to what we talked about previously when we're integrating between a curve and a line. We had this here, didn't we? So we can integrate between b and a, where b is 4 and a is 2. We worked that out. y1 is like the higher curve or higher line, if you like, and y2 is the lower one. So our y1, our curve, as it were, is this one here, and y2, the second function, is x plus 2. And so if we just take this general case and apply it to the specific scenario here, the area we want is the integral from 4 to 2, or from 2 to 4 I should say, of what y1 is, which is minus x squared plus 7x minus 6, minus what we had here, which is x plus 2. Oops, not green, in red. So I want to integrate all of that with respect to x. So obviously this can be neatened up, can't it? To give ourselves a bit more space. I'll show you another way as well in a moment. So between 4 and 2, we can neaten this up. We've got minus x squared, 7x minus an x. That gives us positive 6x. So I need to write that down now, positive 6x. Then minus 6 minus another 2, that's minus 8. So this is what we're integrating. So again, same rules apply. So integrate minus x squared, we get minus a third x cubed. Integrate 6x, that gives us 3x squared. And integrate minus 8, we get minus 8x. And the limits of that are from 4 and 2. So, when x is 4, that gives us minus 1/3 times 64, then plus 3 times 16, because x squared when x is 4 is 16. Then minus 8x, minus 8 times 4, that's minus 32. I'm going to minus off this when x is 2. Minus 1/3 times 2 cubed, that's minus 8/3. Then plus 3x squared. Well, when x is 2, 2 squared is 4, so that's going to give us plus 12. And minus 8x, when x is 2, 8x is going to be 16. So if we just evaluate this on our calculation machines, otherwise known as a calculator, we're going to have this, aren't we? So minus a third times 64 times 64 plus 3 times 16 minus 32, then minus off in brackets minus 8 thirds plus 12 minus 16. And we get 4 thirds. Again, for you class whiz savvy people, we could have done it like this, straight off the bat. Press that button here, type in the limits 2 and 4, 2, 4, and type in the function and let it just do all the hard work for you. So the function we had was minus x squared plus 6x minus 8. So minus alpha x squared plus 6 alpha x, whoops, made a mistake there, plus 6 alpha x minus 8. And we get 4 thirds, exactly the same, but just much easier. So that's one way of doing it. I did mention I'll show you another way as well. So a second method we could have used is to have thought of this in a different way. So the second method, what we could have thought about is doing it like this. So I need to just remind you of what we had from warm-up question 4. From warm-up question 4, what we had is we integrated the function minus x squared plus 7x minus 6. So if we rearrange this blue line here, the curve, it becomes the equation which we integrated from warm-up question 4. And so if we were to integrate this function from between 4 and 2, and that's going to tell us the area underneath all of this curve. It's going to tell us this total area of putting a purple boundary. And like we got from warm-up question 4, that's 34 thirds. And so we know the area of everything bounded in the purple is 34 over 3. Now what we could have thought about, secondly, is, well, how do we relate this whole bounded purple area in relation to this yellow area, which we want to find out, and this shape here, which happens to be a trapezium? Well, hopefully you can see that the bounded area in yellow, I've called it, is going to be 34 over 3, which is what we had from above, minus the area of this green trapezium, like so. So that would give us 34 over 3, obviously. Now the area of this trapezium, just take you back to GCSE for a moment. It's going to be half this length plus that length multiplied by the width. So if this boundary is 4 and that boundary is 2, then we know for sure that this distance here from one to the other, that's going to be 2. So the width of this trapezium is 2. And the heights, well, when x is 2, 2 plus 2, that's going to have a height of 4. And when x is 4, 4 plus 2, this is going to have a height of 6. So the area of this trapezium is going to be half, add together the two parallel sides, so 4 plus 6 multiplied by the width, which is 2. So half of 4 plus 6, half of 10 is 5. 5 times 2 gives us 10. So the area of this trapezium is going to be 10. So 34 over 3, the area of the whole purple bounded section, minus 10, well, 10 is 30 over 3. 34 over 3 minus 30 over 3 gives us 4 over 3, like we had from before. So just to show you the two separate ways you can do it. You can do it purely using calculus, or you can invoke simpler shapes using just basic GCSE geometry. That's often the simpler way of doing things. Okay, final worked example before you try some on your own. This was a real past paper question from yonks ago. This was years and years ago, but it was the real deal. This is what actually came up. So here we have a curve. The curve has equation y equals 10 plus 8x plus x squared minus x cubed. The curve's got a maximum at point A. Using calculus, show that the x-coordinate of A is 2. Now, one of the reasons I wanted to do this question with you is because it's good revision from differentiation about maximums and minimums. So for part A, what you need to remember is a maximum, or a minimum for that matter, is going to be where the derivative function is 0. So let's just do this step by step. So just copying out the function here, like so. We can differentiate this dy by dx. We can find the gradient function by differentiating each term individually. The 10 vanishes, 8x differentiates to 8, x squared differentiates to 2x. Remember the general pattern, do you? The power comes to the front, we knock 1 off the power. So if 2 comes to the front, x squared becomes x to the power 1. Here, 3 comes to the front, and the power drops from 3 to 2. So that's the derivative function. So what you need to remember next is, at maximums or minimums, dy by dx is going to be 0. So we can find the maximums by substituting in 0, because it's going to be equal to 0 at the maximum. So we can set this equal to 0. So 8 plus 2x minus 3x squared equals 0. Multiply both sides by minus 1, so we get it into a nicer looking, more familiar quadratic. 3x squared minus 2x minus 8 equals 0. We need to partition this using the AC method. So multiply the 3 and minus 8, we get minus 24. So can you think of two numbers that multiply to give minus 24, and when you add them together give you minus 2? Well, those numbers are going to be 4 and 6. Of course, you can do this on your class quiz as well. I keep forgetting. It makes it so easy. So 4 and 6. So we partition this minus 2x into a positive 4x and a minus 6x. Then the minus 8, of course, equals 0. So let's just factorize these out. So this has a common factor of x. So x brackets 3x plus 4 minus 2 brackets 3x plus 4 equals 0. Almost ran out of space. So therefore x minus 2, 3x plus 4 equals 0. So this is going to equal 0 when either bracket is equal to 0 itself. So this bracket would give us where x is minus 4/3, which should be this negative one over here somewhere, slightly off the graph. So it's not going to be that root. That'll give us the minimum. So this maximum, clearly you can see, this is where x is positive. So therefore, the maximum must be where x is at 2. So we prove that using the derivative function. This must be where x is 2. This one down here will relate to x being minus 4/3. Now for part B, using calculus we need to find the exact area of R. So what we can do now is use part A to help us. So from part A, we had that the x-coordinate of A was 2. Now it doesn't take a genius to work out this area here. It's going to be the area of a triangle, so I'm just going to call that area T for now. But to work out the area of a triangle, what we need to know is not just the width of it, but the perpendicular height as well. So we need to work out the height of a triangle, which is this here. Okay, I don't want to have that line, that can go away. So we know the function itself. We know that the function of x was y equals 10 plus 8x plus x squared minus x cubed. So we can work out the height of this triangle by substituting in when x is equal to 2. So when x is 2, y is going to be 10, 8x would be 16, x squared would be 2 squared, which is 4, x cubed would be 8. So 10 plus 16 plus 4 minus 8, that gives us 22. So what that tells us is that the height of this triangle must be 22. So therefore the area of the triangle, area of T. How do you work out the area of a triangle? You should damn well know. I'm sure you all do, of course. Half times base times height. So half times base, which is 2, times 22, which gives us 22. So we can use that to help us work out the exact area of R, because using the same example, using the same idea as before, the exact area of R is going to be the area underneath the whole curve from 0 to 2. So we can integrate from 2 to 0 to find out the area underneath all of this. So we can work out the whole thing by integrating this function with respect to x. But of course, if we find the whole area underneath the curve, we're going to find too much of an area, because we don't want this triangle. We just want the shaded bit, not the triangle underneath. So after we integrate the function from 2 to 0, we then need to subtract the area of a triangle, which of course we've worked out, so we've done that bit of work. So the hard work now is just integrating this function. Well, I say hard work, you could by all means cheat now and just use the class whiz, but let's do it with a bit of honour. So integrate this, 10 becomes 10x, 8x, x becomes x squared, divide through by 2, that gives us 4x squared. X squared becomes a third x cubed, and x cubed integrated becomes minus a quarter x to the power 4 in between the limits of 2 and 0, minus the area of a triangle, which of course was 22. So we can put in the limits. So when x is 0, the lower limit's going to be all 0. So that makes it a bit easier. So just substitute in when x is 2. 10 times 2 is 20. 4 times 2 squared. 4 times 4 is 16. 1/3 x cubed. So 1/3 times 8. That's 8 over 3. Then minus a quarter times 2 to the power 4. 2 to the power 4 is 16. A quarter of 16 is 4. Minus nothing if you really want to, which just gives you nothing. Then minus 22. So now we can work out what this is. I'd play this safe and use a calculator. In fact, use a calculator all the time. Why not? I'm just doing this just to be a bit quicker, ever so slightly quicker. I'm probably too slow anyway. So 20 plus 16 plus 8 cubed, sorry, 8 over 3, not 8 cubed, minus 4, minus 0, which I'm not going to bother doing because that's obviously not going to do anything. Then minus 22, we get 38 over 3, which you can leave like that if you want to. If you want to be old school and change it into a mixed number, by all means, if that makes you happy, why not? Could say it's 12 2/3 as well. And so that's it. That's all we need to do. So it's just applying that idea, the area between a curve and a straight line. We integrate 1, then integrate with the other, or try and look for simple shapes. For example, in this case, look for triangles. So it's over to you guys now. I want you to have a go, starting at page 304, exercise 13G, the whole damn thing, please. Try that. Give me evidence that you've done some work if you can do, pretty please. Email me if you're getting stuck, drop me a message, or if you want to leave a comment in the comment section, by all means, that's just as good. If you finish those or want more practice, there's always a mixed exercise after. So go on with your work, do your best, do work hard, try all the questions, and if you're stuck, do ask. Okay, so you'll hear from me again in the next video. Until then, take care and keep safe. Thanks for listening. Cheers.